All right. So today we will be discussing performance optimal read-only transactions. And these are my sketchy handwritten slides. So this is basically like a presentation that's going to happen in 3 acts. We're first going to go over like the performance optimal sort of theory that they have, and then the actual concrete system. And the concrete system is split into 2 pieces. There we go. The like doing read-only transactions at causal consistency, where you only get to issue single writes, and then doing read-only transactions plus you get to do transactional writes. And these are done in 2 separate systems and benchmarked differently. We will discuss them separately. So for the first part, we have this NOC plus S, or just NOCS algorithm, which is, oh good, I can move this out the way. So this is a theory that says that if you have a system and you want it to be non-blocking, so like when you issue a read to some server, it can just immediately return your result. You don't have to wait for anything. You want one round trip. So that is, your read is just you go to a server, you get a response. There's no like you have to go to like a server and then go to another server afterwards. You don't go to a server and then the server has to internally go to someone else. It just immediately has your data for you. And you want constant metadata. So regardless of how many operations you issue, you just need to have like a small constant chunk of metadata that you hand out. And you don't need to do something like, all of your writes need to contain a description of all of your other writes. And if you want these 3 things, then you don't get strict serializability. There's no way to get strict serializability if you want these things. You can look at this in the contrapositive sense and say, if you want strict serializability, then you need to have one or more of these 3. You either need to accept that you will need to block in your reads at some point. You'll need to accept that that will require more than 1 round trip of communication, or that you're going to need to hand out metadata that grows with the size of the operations and workload of the database. They have a proof of this. And their proof, I think if I abstract it out correctly, is basically saying, like, if I have 2 clients and 2 servers, and each of my client issues 2 operations. And let's say like client 1 issues write 1 to server 1, client 2 issues write 2 to server 2, and then they both send an operation to the other server that arrives second. In isolation, server 1 will see this as the client's write 1 is ordered before the second client's write 1. And then server 2 will see the opposite. And basically, like their argument and discussion here boils down to the fact that it's linearizability's real-time ordering that's the problem. Because the real-time ordering is the reason why server 1 had to order like the client's write 1 before client 2's write 1, and why server 2 had to do the opposite. And so like resolving this and basically getting this sort of conflict situation to not happen would require either like, blocking for some sort of communication to happen, doing another round trip between the servers, or something to like get the exact ordering figured out. So basically they turn this into a description of a solution of, if you want to build a system that satisfies their like NOC criteria, then you need to give up linearizability. And the next strongest thing that they can offer is process ordered serializability, which we'll discuss later. The ordering needs to come from somewhere in this system, and the only way that you can do that without blocking would be like check the clock, which means linearizability. You can't do that. So the ordering is provided by clients. And then if the servers maintain a multi-version database, then that means that you have versions with known amounts of data that you can just always immediately hand out without having to block in anything else. So the like 10,000 foot overview is the rest of the paper is about designing a system that works like this. So single write port, which sounds like a drink, but it's not. They implement this on Scilla. So a real like quick overview. ScyllaDB or Cassandra, because they implement the same protocol, is a consistent hash-based wide column store. It is single versioned. It is eventual consistency. It resolves everything based on last writer wins. So there's a timestamp associated with all data. That data eventually gets gossiped around in anti-entropy, and everything eventually decides on basically accepting the last write that happens. Scylla is an optimized C++ version of Cassandra. They chose Scylla because then a large part of the argument in this paper is that implementing port is low overhead. And if they choose something that's already highly optimized, then the overhead that they add will show up notably in the evaluation. And if there's not a lot of overhead, then they have a very strong argument that their described system does not add much overhead. And in not adding much overhead, then you literally just get a fast Cassandra that has read transactions. And so it's a direct improvement of the base underlying system. You get two operations, basically. You can do reads and you can do writes. Clients are providing the versions, that is SF here for stability frontier, which we'll discuss in a moment. When you issue a write, you basically take whatever your client version is, add one, and that's the version you submit to the server. Servers do operations, they generate a reply, which in the case of the read is a value on it, in the case of the write is just an acknowledgement, and then they give you back the maximum version of anything that they've seen. So there's basically a ping-ponging of versions between the client and the server. A client maintains a map for all of the servers, the maximum version that it's seen from any server. The version that it's seen from any server. And so in this case, right, we've seen up to some version threshold for server 1, up to some version threshold for server 2, up to some version threshold for server 3. And we take the minimum of all of these, and we call this the stability frontier, which sounds like a Star Trek episode. And if we issue all of our reads at the stability frontier, then we know that every server we could possibly talk to already has data at that version. And so it would not need to block and wait for clocks to advance or anything. It just immediately has an answer it can give us. And so when we do reads, we always do the reads at the stability frontier, which gives us the most recent data at a version that we know that all servers can immediately serve a reply to. Servers basically have a multi-version map of all of the writes that happen. And they keep track of this at some, so we start off at version 0 and we go up to version something, and then it becomes B. And at any point in this, a client can show up and say hey, I'd like to read keys 1 and 2 at version this. And then we look at it in our memory and we be all right, so this is your snapshot line and this is what you want. The max version is just the maximum of anything that the client has shown up and talked to it about some key. So in this case, right, we've seen that we have a write of B and it goes up, and therefore we know that this is our max version. So max version goes from server to client. That's how clients learn about advancing versions across a bunch of servers. Clients take their stability frontier, they do a bunch of reads at it. Whenever they want to modify the system, they add one, they hand that to the server, which is how new versions are actually generated in the system. All right, there's some complications here. Let's say that we have a server with one key. That key is 5, or that key is A. That key is key 1. It has a value of A. It was written at version 5. Some client shows up and it says, hey, I'd like to do a read of this key 1 at version 15. That's fine. We look at our memory. We see that nothing's at version, we go down from version 15. We find A at 5 and we're great. We can return A. But there's this thing where we've now returned A to a client. And so if it shows up again, we should return A for anything between 15 and 5. So we record that a read happened, and we maintain the maximum version that we've seen or the maximum version we've seen for reads at any given, for every single key. And then if a write shows up, and the write wants to be the timestamp that the client gives us for the write is in the middle of something where we've already promised a read, then we basically promote that write, give it a higher version than what the client asked for. So in this case, we would start at 15, or we'd start at 16, basically, because we've already promised that between 15 and 5, we will always give the answer of A. And so we start at 16 and we say, all right, v now exists at 16. And then we return v max of what should be 16 here because my versions didn't quite line up. It's fine. So there's this write promotion thing of if you do reads and then you do a write and your write intersects the version range of what has already been read, then we take that write and we sort of like pull it up in version space. And then we give it a new higher version and we've now promoted the write. Sort of in the opposite direction, there's a write omission sense where if we have some key and we do a write to it and that write is at version 10, we can now say that like, all right, we've accepted your write, we accepted your write, the maximum thing we know about is 10. If another write shows up and that write happens at version 5, then we can basically omit it because we can say that what we did was promoted this write to exactly the version 10 where we accepted A, and it was applied to the database immediately before A. So we accepted it and it's okay, but there's no version that you can actually read that sees it. And between like these two things, we basically did a thing where like we have a known way to be able to order any two writes, because either like, you know, we accept things in increasing version order, and then we just apply them sequentially. We accept them in decreasing order, and then we just get to omit a bunch of writes. And basically resolves like the issue of linearizability, trying to assign versions in a way that conflict. One of the things to be aware of with port, and that they discuss a bunch in their evaluation, is that with choosing this like stability frontier, there's an issue of staleness, right? Because like clients are providing a read version to a server and the server honors the read version. And so I've basically broken this down into like, there's two different sorts of ways that you can look at the staleness. One is like a known staleness where because of your stability frontier, it's possible that like, you know that server 3 has like accepted a bunch of writes potentially to what you're going to read, and that you're issuing a read version at something lower than that. So there's like a known amount of version advancement that you're potentially missing out on, and you as a client know that this is going to happen. And on the other side, if you're a server, like it's still possible that from the client's perspective, like it's issuing it, you know, the most recent thing, but you've accepted things because there's other clients concurrently. So to the client, like there's some unknown amount of staleness. And between these two is you get this like, you know, wonderful non-blocking constant metadata one round trip thing, but you have to accept that there's going to be some staleness in the replies that you're getting, and they'll no longer always be of the most recent version. So that's basically like the single write or no write transactions port on Scylla. So I call this Portella DB, which I think is the best wordplay that I have in this presentation. And like overall, like this looks quite good. And you can look and see that basically like when we compare the overheads of like Scylla and Scylla port, like these numbers are all pretty close. Like I feel like they did exactly what they promised. They have a very low overhead addition on top of a base system that then provides them with read snapshots. And I'm sure we'll come back to this during the discussion section. For the write transactions part, they implement this on top of eiger. Eiger has the same sort of like, there's a logical clock on the client and a logical clock on the server, and they do the same sort of like ping-pong versions between the two. How eiger does snapshot reads is that basically like we have some keys with like changes over time. And when you do a read, it gives you back the basically like your first round is the most recent value, and it gives you the version range that it knows about. So like in key 1, server 1, the maximum version the server knows about is here. The commit was done here. And so it gives you like the answer is B, and this is the version range. And you get this from each server. So you then go back and you look at all of the answers that you've gotten after your reads, and you try and figure out if there is a like consistent line that you can draw across such that you intersect all of the version ranges. And if so, then you know that these actually did come from a snapshot of the database. And then you can immediately return that to a server. If you don't have that, then you need to go back and issue more reads at specific versions in order to be able to get a consistent snapshot. They do write transactions basically via a two-phase commit process where you first mark values as uncertain and then you mark them as certain later. Reads which encounter uncertain writes from transactions can take 3 round trips. And this is one of the major things that Port is trying to fix with Eiger. So Eiger Port does writes via, we have some starting thing where we have writes that start at A and went to 10 and 20 is what the servers know about. And we say that we're doing a write at something. So the server 1 records that this is a pending write at 10. Server 2 records that this is a pending write and it needs to promote that write to 20. The two then enter into their always agreement 2-phase commit step, where basically server 2 sends a vote to K1 that says, my timestamp that I prepared at is 20. And then, so now server 1 knows that it basically goes and collects all of the votes and then takes the maximum timestamp across it, and that becomes the commit timestamp. So in this case, the commit timestamp is 20. And so we then propagate that commit from server 1 to server 2, and we set pending to false. And now we have, starting at version 20, that is when B is committed. And we have this version range of uncertainty that is the thing that basically clients will never see. And then we get to hand back that our Vmax is now 20. There's some trickery that's going to be involved in the maximum version that a server will return is a version that has no pending writes. So in this case, commit timestamp is 20, so we can return 20. If there was some other write that was still pending at version 15, then we would hand back version 15. For reads, we get into this interesting process ordered serializability case. So if we have some keys and we want to read key 1 and key 2 at version 15, so up here-ish. All right, let me explain this diagram a bit better. So key 1 has some pending write that starts at, we're going to say version 16. We've already accepted on server 2 key 2 2 writes that are this particular client's writes. And so what process ordered serializability is trying to maintain is basically transactionality, and from one particular process, a sort of look as if the database is actually linearizable, but we get to give different clients different answers. Or sorry, I should say not linearizable, I should say read your write semantics. So for a particular client, their operations are applied in order and they get to see that. But not all, all clients will not receive the same view of the database and the same view of what writes were applied at what points in time. So when we do this read, we now split out into 2 cases. In the first case, right, is that the C and D are this client's own reads. And if that's the case, then we basically take the maximum of anything we've seen. We basically reach up in version space and claw back the client's own writes to the read version that it requested, because we should have this sentence that if a client writes C and it writes D and then it issues a read at its stability frontier, it should see D. And so in this case, the answer that we would return would be A and D, and this Vmax we'd still return as 15 because we have a pending commit that starts at 16, so we can't return anything higher than that. So we're still limited to a stability frontier, or we still limit the client to a stability frontier of 15, but we need to still return this write D that might have happened at version 18. If C and D were not the client's own writes, then we basically totally ignore them. We just do the exact, we draw a line across it version 15, which gives us A and B. And so we just return A and B with a maximum version of 15 still because of the pending right. So this is where we get into this, like we present two entirely different views of the database, depending on if the rights are your own or not. And that changes for each client, which means each client gets their own different, like with certain rights clawed back into version time. With this, there's an even more complicated thing. And if I got anything totally wrong in this presentation, it's definitely this topic. What I drew was this, we have this wonderfully nice stacked A, B, C, and D. It's possible that these all came from their own write transactions. And that these write transactions, like what I have drawn is like, the nice clean breaks is the commit timestamp. But there's actually a version that this particular server prepared this write at. And so if we try and do a read, and like what we did is like our maximum version is D, that write of D is actually concurrent with some other transactional write. And we can look at this via basically taking the commit timestamp versus the time that like the sysclient write timestamp, which I think is actually wrong. The timestamp at which that local server prepared. And if this overlaps the commit of another write, then we were concurrent with a write transaction from our own client. And so we basically need to like go through and find the correct write out of this concurrency that gives us a consistent snapshot that will always be correct and include all of the writes that other servers that are doing this calculation would return. And again, this is a thing that only applies to our own writes. If at any point in time in doing this, like trying to basically like extend our reads backwards such that they become concurrent with more things, is only a problem that we have when it's our own reads, because we're doing this basically like clawing our own backs for read your own, or clawing our own writes backwards in version space to maintain read your write semantics. If these are other clients' writes, then they still they exist from the commit timestamp onwards. And this sort of like logic doesn't exist. And the whole thing of what this is trying to do is like make it so that like if some client does a write and sets like key 1 to be and key 2 to be at some version, then if you go back and you do like a read of key 1 and key 2, you should make sure that like that's what you see, regardless of any other concurrent transactions that are going on. And then evaluation, which again, like looks pretty nice, right? Like they show that they have a very nice like reduction, basically the overhead. They can get more performance because they're doing less round trips. And so this seems nice. In both cases, like their staleness, they explicitly measured, which isn't like that terrible, but it's still like you have to be able to tolerate staleness. There's a bunch of discussion in the paper of ways to try and better control and tolerate staleness. That like, if you have multiple clients on one machine, then you can sort of like pool their notion of the various versions that servers are at together to try and like share all of the highest version watermarks between all the clients. And so there's a bunch of related work. The largest comparison that they do is between, there's a previous paper on Snow, which talked about latency optimal systems. These two papers have the same first author. So the difference that they draw here is basically like this paper is trying to establish bandwidth optimality, right? Like with our constant metadata, like we want basically all of the bandwidth of the system to go towards the writes that we're doing. And Snow was focused more on how do we get like theoretical low latency. There's other papers that are in the same sort of like vein and examination of systems by other authors. I'll highlight there's a distributed transactional systems cannot be fast that makes the same sort of like at a very high level makes the same sort of feeling of arguments as what's made in like Snow and Noc. There's a couple other systems that have pretty sort of related implementations and kind of similar goals. So I think Occult and Paris are sort of the two things that I recommend to look at there. And that's all.